Now, I want to show you these four pictures together as well, because we don't have the time to go into every fable. But what you see, you know the zebra by now. You know the zebra well. Now, what do you see here? What happens there? Normally when you have two pipes of water, a pipe of water, in the water here and in the water there, does it flow? No, because there's no difference in pressure. Does this flow? Why does it flow? Because the black and the white. What happens with the black? The water gets hot. When the water gets hot, it expands. So, when we do this with children of 5 and 6 years old, they know this works. So a 6-year-old will tell you the water will flow from there to there, because they understood the zebra. So we don't have to ask them, did you understand the zebra? We don't ask them. We give them that story, and then when they say, oh yes, this works, then we know they understood the zebra and this. But the complexity of this is higher in the mindset, because we have a physics law that says if there is the same pressure, then there will be no flow. But now, even if the same pressure, there is flow. Because in the laws of physics, we have two main parameters: pressure and temperature. That are the two. And so unfortunately, when we're teaching physics to our children, we only teach pressure, and then we teach temperature. But both of them together we don't do. And as a result, in real life, now when children know this and that, they know the basics of physics. Because they also now understand the difference between gas and air, gas state, liquid state, and now they're going to be ready for solid state. So I can prepare them to think about solid state physics, gas-based physics, because they know these two stories. And it's amazing how fast the children make those connections. Since we have not been exposed to it, it takes us a little bit of time to adapt. Now, watch what happens in the fable. I put here, in the zebra fable, I put in the painting, in the drawing, I put the butterfly. Butterflies, children love them. And I know here in Taiwan you have incredible biodiversity of butterflies. But the children love the butterflies, but the butterfly doesn't fly, it's a windsurfer. But in this story, we don't say anything about the butterfly, but the children see the butterfly. And they think, they register. But then we have the story about the butterfly and the trout. And the story of the butterfly and the trout is like, I'm a windsurfer, says the butterfly. And of course, the child immediately connects windsurfer and remembers that picture. Because this picture is one of the most popular pictures of all the pictures we've made. Children love this one. So since children register this picture, and they now know that the butterfly is windsurfing, but that's windsurfing, the trout is water surfing. So now again, you see we're reinforcing only with the view, only with the images. Windsurfing, water surfing, it means physics based on liquids, physics based on gas state. And that allows us to jump over a lot of the difficulties and the complexities of teaching physics. You're a physics professor, right? Yeah. So we very often have it difficult to get the children to think into these worlds, but they love the idea that the trout goes against the current. Now, if we have to explain on the basis of fluid dynamics to the children, how does the trout go against the current? It's even difficult to explain to adults. It's not easy. But what is interesting is that, and I don't go into detail because we don't have so much time, but the head is very important. And it's the shape of the head of the trout, which actually from the front looks like an egg. And when you have the perfect geometry of the egg shape in front of the trout, then you realize that the trout can generate this, provided it can play with its gills. And by pushing, so when the trout wants to go forward, it just opens its gills. Can you imagine? Just like this, and boom. So it doesn't have a strong tail. That's the salmon. The salmon has a very strong tail. That's why you love to eat the salmon, because it's very muscular. The trout never has too much meat on the tail. It's quite a thing. Most of us, we don't even bother eating the tail. The tail of the trout, of the salmon, we eat everything. So this capacity to generate fluid dynamics to propulse forward is a very, very unique phenomenon that is part of what we call nonlinear mathematics. Now, we never teach nonlinear mathematics to children, not even to teachers, not even in university, unless you're majoring in mathematics and you have a specialty called nonlinear mathematics. So what we're doing is actually introducing the children to the nonlinear mathematics. We don't say we are teaching you nonlinear mathematics, because when you say we're teaching you nonlinear mathematics, everyone closes their ears and the mind. But by being able to introduce them to nonlinear mathematics, we're introducing them to the only way that nature works with math. Nonlinear mathematics means that 1 plus 1 equals 6. 2 multiplied by 2 is this time 37 and next time 57. Nonlinear mathematics is very complex to calculate and to grasp, because we are in straight lines and circles. But we need to open up the minds of more. So here I'm showing you 3 fables, because these are the same fables, these 2. But with these 3 fables, we're doing an introduction to nonlinear mathematics. We're doing an introduction to solid-state physics, liquid phase physics, gas phase physics. And we all know that this is very different, but the best we very often can teach our children is gas state, liquid state, and solid state, and the temperature ranges. But here, we really open up what we call, in English, the Pandora's box. You know, you open up a box, and so much is coming out of there.